Hi everyone, welcome to my GCAP 2023 talk, The Puzzle Sequencer, a state machine for puzzle flow. I'm Kath Nix-Carnell. I'm a senior programmer with Mighty Games, and this is my first ever talk. I've been a programmer for about 19 years now. 7 of those are in games programming, and it is only now in my careers that I have finally come up with something that I can consider myself enough of an authority on that I can talk about it for an hour without stopping. Firstly, I would like to acknowledge the traditional owners of the lands on which we meet today, which is the lands of the Wurundjeri and the Boonwurrung people of the Kulin Nations. Because I work remotely, I would also like to acknowledge the traditional owners of the lands on which I work, which is the lands of the Dja Dja Wurrung people. I would like to pay my respects to elders past, present and emerging, and I would like to note that sovereignty was never ceded. The first question I think people are asking is, who is this talk for? This talk is targeted at intermediate Unity programmers. I will be using, of course, a fair amount of programming and technical terminology, so if you don't have any familiarity with the basic programming concepts of composition, inheritance, interfaces and polymorphism, then at least some of this talk may not land so well for you, but I always have a lot of fun at GCAP when I go way outside my lane, so knock yourselves out. But also, I will be using a fair bit of terminology that other people use with different terminology. I started out my career as a JavaScript programmer, and so I will be using the terms function and variable instead of method and property. Now, I do have a fair bit of content that I want to cover, so I may talk quickly. Also, I'm a little nervous, and I may not pause too much. But of course, the talk is recorded. I will do my best to have some slides online for you, so you will be able to come back and have a look over if you feel like you missed anything. So that is our introduction. Let's get stuck in. The puzzle sequencer. Today I'm going to share with you a puzzle creation system I designed for an as yet unreleased game that is still under NDA. It is a narrative puzzle game. We used the Yarnspin engine to handle the narrative for our game, and we found it to be super flexible and ideal for our purposes, and you can find it on the link on this slide. So next I'm going to explain a little bit about what the puzzle sequencer is, but mainly I'm going to take you through some puzzles that I made using the system and with a deep dive into the code to see how all the constituent parts come together. So firstly, what is it? It's a system, of course, that's designed to create and run a variety of different puzzles. It relies on lots of component reuse. Of course, polymorphism is our friend here. And it's a lot easier to show than tell, which is why I'm going to focus heavily on examples. I also want to cover really quickly, but what is it not? The puzzle sequencer has not been created with the intent of releasing it as a standalone tool or plugin. This talk is covering the systems design approach that I have taken with the intent of empowering all of you to make something maybe better than I have. The next question people will be thinking is, why did you make something like this? Because there are so many solutions out there, why would you roll your own? And essentially in our game, we were not in a position to be able to use much in the way of external libraries. And so basically everything we wanted to put in our games, we pretty much had to make for ourselves. We also had a project requirement to keep the weight of our game as lean as possible. Leaner than that. So making our own system was a really good way to control the system's weight and speed. We were also working to fairly limited timelines. My first look at the prototype team's work was after last year's GCAP, and we have submitted this game now. So that's the timeline, less than 12 months. We actually got it done in 8. Because of that, we didn't have any kind of outline of exactly what puzzles were going to be in the game, and nor did we have any kind of dedicated tools or pipeline where we'd be able to figure out everything that we needed and then make it available to our designers ahead of time. And so we needed a system that was going to be flexible and scalable enough to grow as needed during the development life cycle. We did also have the benefit of knowing that our narrative was going to be largely linear in nature, with a high number of very self-contained puzzles. This removed the need to support many different puzzles that had interdependencies upon each other or that might exist in parallel partially completed states. And that meant that we could control that and make a simpler system. I do think that if someone wanted to make a game that had those sorts of things supported. This system would support that. It would be mainly in your save state and not on this system, but you'll see how that works as I get to it. But basically, we had to get started fast. We had to build as we made the game. Now, I'm going to do a couple of shout-outs to a few specific colleagues here. And my colleague, Unit 03, was involved in the initial ideation for this system. They are amazing at systems design, and they have an incredible knack for seeing the simplest path through a problem. My mentor, Andre, who has always been available to help with anything I'm stuck on, he's right there. And also, everybody who ever had anything to do with the puzzle sequencer while working on this game, which is Michele, Shamir, Sam, James, Clinton, Russell, Ryan, and Darcy. This entire system is better because of the input of everybody on the team, so thank you all so much for your help. So I'm going to switch over to Unity now, and this is the terrifying tech part, and I'm going to show you a puzzle that's actually running off this system. And I can promise that these puzzles are absolutely, definitely from the game we made. They are certainly not puzzles that we invented just for the purposes of this talk. Just give me a second. So here we have a really simple puzzle that you might see early on in a game. Our player has found a mysterious cat statue, and I would like you all to imagine that I said those words with capital letters. So, as I said, in our game, each of our puzzles is quite self-contained, and we managed this by containing them within a Unity scene. Most of our puzzles didn't have any kind of flow-on states with each other, but when we did need to support that, we made sure that the way that the last puzzle looked when it finished was the same as the way the next puzzle started in the game. And so this, of course, allowed us to reduce the bugs in our system while also having a cohesive experience for our players. So I'm going to really quickly run this puzzle now, and we're going to see how to solve it. And I just remembered I haven't cleared my player pref, so I'm going to do that now, because otherwise you'll all get spoilers. So we have this really cute cat statue, which we can have a look around and rotate in the game scene. And it's a very cute cat statue, but unfortunately our player knows there is something inside it. So we're going to break it open, just like this. And that's the first part of our puzzle. So we can see after that we had a bit of a delay, and then this little button here lit up. And so it seems like we're going to tap that, and this here is the finishing state of this particular puzzle. I made quite a simple one early in the game. So we're going to have a look now at how all of this was constructed. So firstly, I want to just make sure, can everybody see the Unity Inspector enough? Because I know it can be very small and you can't change the size of its UI, unfortunately. So everyone's good? Lovely. And the first thing we have here is the puzzle sequencer component itself. Now, this is the parent state machine that is controlling the individual parts of the puzzle. The first thing that we can see here in our puzzle sequencer is the concept of a puzzle side. And because of the narrative of our game, we knew that we had our puzzles would be taking place using a regular shaped object, using a known number of sides, and so I named these puzzle sides. I think if I was going to make this again, I would probably call them like puzzle steps or something like that, but puzzle sides is where we got to. So essentially what the sequencer will do is it moves through these elements of the array in sequence before moving on to the next one. And it is a fairly simple system, as I said. But once all the puzzle sides are complete, the next thing we can see here is the sequence finisher. Now, this was a smaller component-based system where we had different effects display for different puzzles. Some of them would spin away from the player, some of them would fade to black. The effect in this particular puzzle you just saw was that the bracelet floated. And the idea was with this, of course, that each of our puzzles could control how they finished. And we're going to have a look at these in a bit more detail. You can see we have our three puzzle sides. The first one is called Show Objects in Order. Then we have one that's called Wait Some Time, and you can see it's got a type of wait a while. And then finally we have a Win button, which has a type of cumulative taps. So we're going to start at the top with the Show Objects in Order. So this was a puzzle side that would basically just turn off and on game objects in order. And we're going to have a dig into how that was actually constructed. So you can see we've got a couple of different sections here. We have our puzzle finished actions, which we have our helper restore events. We have our juice, which is of course very important. And then we have our puzzle parameters. So sorry, I've lost my place. So in the puzzle parameters, we just have this one array here, which is our tap states, and now these were the objects that we were showing that created the appearance of the statue cracking open. And essential hookups, of course, hold things like a collider and a camera to use for raycast detectors. So you can see that puzzle finished actions look similar to the puzzle sequencer, puzzle side array as well, and they did work very similarly, except that this didn't really wait for anything to be finished. It just went through everything and fired them off in sequence when the puzzle was finished. And that is, sorry. So they all fire in sequence and the puzzle side is marked as solved. So the next thing we're going to do is we're going to hop over into the code. So this is our state machine controller, the puzzle sequencer class. So we have it set up as a singleton class, and I'm going to move these because I can't see them properly.
Can you zoom in?
Can I zoom in? No, unfortunately I can't, or I can pop up the font size a bit. Is that better? No worries. Let me find my place again, 1 second. So, we have it set up as a singleton class. Don't worry about the singleton mono base class type. That's an internal Mighty library that we use to have a standard way to instantiate and access our singleton instances. However you need to create a singleton will work just as well, at least I hope it will. So we have, of course, our puzzle sides stored in an array here. Now, I'm going to really quickly hop over to the puzzle side parent class to point out one of the really key things about the puzzle sequencer, which was that I leaned very heavily on inheritance through the whole system. I'm going to go into a little bit more detail about the benefits of that later, but I just wanted to point that out really quickly for now. So it's the same thing with the sequence finisher. It uses the parent's class type here to keep everything properly neat and abstracted. Now I'm going to skip over the next couple of variables here, and we're going to head down to our awake function. So the first thing we're doing here in our awake function is that we're grabbing our puzzle's state. We're just getting a couple of really simple bits of state here. And one of the things that we did in our game to help keep our overall footprint as small as possible was to reuse our game state keys. And I know that this is a risky thing, but we were able to get away with it in our case because you couldn't have two puzzles open at any one time, and so there was no real risk of the puzzles getting into any kind of state that they didn't understand. So we're also getting the addressable name for the puzzle side, and we're actually not doing anything with it after this point. It's just getting it for debug purposes. Now I'm going to skip over the next couple of lines there and hop down to here, which is the next major thing you can see that we're doing here is that we are iterating over the puzzle sides. And you might notice that we're using a decrementing iterator in this case, and this was a bit of a hack solution. I found that when I first made this and I tried to initialize the puzzles using an actual incrementing iterator, then puzzles that might have shared game objects or colliders would sometimes end up in unwanted states, and so the easiest solution for that was to start at the end and work backwards. So we're iterating over all of our puzzle sides, and we're calling their init functions. And this sort of thing was where an interface and some inheritance was extremely useful, because using an interface here means that this function must be implemented. You can't have it any other way. But also each of our subclassed puzzle sides off the parent can decide what it needs to do in that particular init. So the next thing we're doing is a really simple check of are we partially complete with this particular puzzle side, and with this particular puzzle, not the side. And we did need to support partially completed puzzles because of the way that our hint system worked. When we loaded into our hint system, the puzzle scene was loaded in its entirety and then reloaded back in when the player came back to the game. So when we have a partially completed state, we know that at the outset because we have an index greater than 0, of course. So in that situation, what we're doing is we're going up until the puzzle side before the one that we actually want and just setting them to display as if they had been completed. I'm going to skip over the next couple of standard functions again, and the next thing I want to point out here is the advanced sequence function. So how that we used this was when each of our puzzle sides met their individual completion requirements, they call back to this function directly. You'll notice that it's a public function. And I know there's probably better ways to do this. This is just the way I decided to do it. And this is where we're checking to see if the puzzle sequence is actually finished and whether we need to complete the sequence or move on to the next puzzle side. So you can see here that rather than incrementing active puzzle side first, we're checking against what it would have been if we were to increment it, and then we decide to increment it only if we have more puzzle sides to use. And then, of course, we save our state. The next thing we do is a bunch of reset stuff. And sorry, I've skipped over the finish sequence function, which does a couple of small things here, but mainly what's important is that it calls to our sequence finisher component to do whatever thing we set that up to do. And then after that, we do all this reset stuff, which is, remember how I said we were reusing our save state keys? This is where we reset the contents of those keys and make sure that we have everything in a nice clean state ready for our next puzzle. So that is the entirety of the puzzle sequencer base class itself. The next thing we're going to move on to is the puzzle side class. So the first thing we can see here in our puzzle side class, in our class declaration, is an interface. So this, of course, helps us describe the structure of our class, ensuring that these functions are available and must be implemented, and we don't have to use overrides in every single instance. So we're just going to have a really quick look at this interface, which is pretty much what you might expect: save progress, restore progress, initialize, begin, complete, and display completed, which of course is different to actually being complete. So we're going to have a look at our variable declarations here in the puzzle side class. So we have our array of puzzle finished actions, which is also a really super small parent class. So I'm just going to pop in there really quickly. That's also using an interface, and all we have is a declared body that has to be declared because, of course, of the interface. Now, I think I used virtual functions here because the puzzle sides needed to be able to override these functions, but also I wanted to be able to not do that when I chose to for whatever reason. If one didn't need to do anything, you just don't implement it, or you'd implement it with an empty body, and that was all I needed to do. So the next thing we're going to get down to is we're going to start seeing some of the implementations of those functions from the interface. Now, obviously in our base class, we don't want to do anything with save and restore progress because the parent class doesn't have any idea what kind of state the puzzle side needs to be in. And so we have to implement it because of the interface. So we have empty bodies for those. And the next things we have here are the init and begin functions. So we are keeping it fairly simple at this high level, and what I'm doing here is just setting up some simple booleans that are going to be used when we actually go into the full implementation of one of my puzzle sides in a minute. Now, the next thing down, we have our complete puzzle function. So this is where we're doing things like we are iterating over all of our finish actions and firing them off. And this is the call that I mentioned just before, which is back up to the puzzle sequencer parent class to advance the puzzle sequence. And the next thing we're going to go into is, display completed puzzle as well. It's complete, so similarly in display completed puzzle, we're calling back to those finish actions because those were often putting things in place ready for the next puzzle side in the sequence. And we've also got something here which I will go into in a lot more detail later, which is puzzle was restored. So the next thing we're going to look into is the implementation of that show objects in order puzzle side that we saw in our cat statue puzzle. So in our variable declarations here, we just have a really simple array of game objects. And I'm just going to bring our attention back over to Unity quickly to show us what this looked like in the inspector. Oops. One second while I find my place again. Right, so I probably could have made a custom inspector for all the puzzle sides that kept things like puzzle parameters at the top of the inspector and finish actions at the bottom, but I didn't have time. So we just had to get used to how things naturally lay themselves out in the default inspector. But in this particular puzzle side down here in the puzzle parameters, which I just closed, this is where we have the array of game objects that we saw. You'll notice that we do have a bunch of different states here, which is how we showed what the various objects looked like as the statue cracked open. So in here is, of course, this is the really important stuff of how our puzzle sides generally worked. I'm only showing this simple one as an example. Now, all of our puzzles did a really quick check in their init to make sure that they were properly initialized. And I think I've actually skipped over something. One second. I have. So one of the important things here is that you can see we're now getting away from public and virtual variables and functions, and we're starting to get into private ones that are only relevant for this specific puzzle side. So, of course, this sort of thing was where inheritance started becoming really useful, because none of our other puzzle sides needed to care about this particular internal state tracker. And then, of course, in these initialized functions here, we're setting that internal state tracker to 0 because that's the initializer, not the begin. And then we're calling back up to our base parent class, which is, of course, what we want to do with good inheritance. We're going to move on to the begin puzzle function now. So they all do this quick checkup just to make sure that they have actually been correctly initialized. And then they set some of those bools that we saw that were up in the puzzle side, init and begin puzzle declarations. Now, in this particular case, you can see the next thing we're doing is we're enabling a tap collider. Now, we did things like this because we did a lot of sharing of things like tap colliders, game objects, those sorts of things between different puzzle sides. And so we wanted to make sure that these were turned off when we initialized the puzzle, which was, of course, that decrementing iterator we saw back in the puzzle sequencer. And then we only enable the colliders exactly as we need them. Now, most of the next stuff is mostly state bits and pieces. And then we're doing a bit of a completion check here, just to make sure that we haven't gotten ourselves into any kind of dead end to obviously avoid some bugs there. Now, we don't have a whole lot going on in our complete call. We're just disabling our collider again to keep things nice and clean for later puzzle sides. Similarly, in the save progress, that's pretty self-explanatory at this point. The restore progress, interestingly, we don't need to get hold of the state in this particular case because we already had the state from our initialize and our begin puzzle calls. So we don't actually need to get hold of any state there. So all the restore progress, apart from a bunch of logging and all sorts of other things there, all it really needs to do is call to update tap states. Then that's obviously also specific to the functionality of this particular puzzle side. Moving down, we've got a continual check here for a tap collider, which I'll go back into in a little more detail in a minute. But what we want to look at now is update tap states. So there's really not much to it in this particular case. We turn off all the game objects, and then we activate the index of the one we are currently up to. So again, this sort of thing is why inheritance is a really good idea here, because not all of our puzzles would need any kind of tap state detection like this. And so they could just take care of their own things, and all the other puzzle sides took care of their own things, and nobody ever had to talk to each other, and that was really nice. And display completed puzzle does pretty much what you'd probably expect in this context, which was to disable everything and then just enable the last one, because that's the final one, and that's displaying as if it had been completed. Now, I did say we were going to go back to the tap checking, which was a simple mouse down. We make sure we're tapping, not dragging, and then we're moving on to some raycast checks to see if we hit our colliders. And then we are incrementing our our internal state tracker and then calling back up to update tap states. Now, that is actually the entirety of this particular puzzle side, but we do have a couple more concepts to cover. One of the first ones was the concept of finished actions. So these were really super small components that only did exactly what they needed to do. In the case of the show objects in order puzzle side, this is the one that displayed the bracelet after we cracked the statue open, and obviously the statue actually was bigger than the bracelet, but I included it for academic purposes anyway. So similar to the show objects in order puzzle side, this also has an array of game objects, but instead of being shown in any kind of order, they're just all shown at once. And there's another little component we could see there, which was a different one, which was really super simple, less than 20 lines of code, I think, actually. I'll hop into that one really quickly. Here's a sound key, play it. That's it. That's all it needed to do. But you can see that it also subclasses off puzzle finished action as the parent class, which means that we have access to this specific function, and then it handles whatever independent functionality it needs. So that is how the sequencer and the puzzle sides worked together. And the next thing that we're going to move on to is the final big concept that actually helped glue the entire game together. So we've basically looked through almost everything in this first puzzle here, but the one thing we haven't really looked at too much yet is this win button. So in our sequencer, you can see with the win button, we have a puzzle side called cumulative taps. And I can tell you something, trying to name these puzzle sides was such a time, because I had to come up with names that were specific and generic and flexible, and also communicated everything to our designers. So we came up with some truly ridiculous names as a result. So it's really, I'm not going to go into the code for this particular one because we don't really have time to go into it, and I think most of what can be understood about the system can be understood with the other puzzle side that we just looked at. But what I want to look into here is active state game object. And now I'm actually going to approach this from the perspective of someone who may have just come onto the team, who has been told, hey, here's this system we use to make our puzzles, have a bit of a poke around while you wait for someone to come and talk to you later. So we're going to have a bit of a look in here. And the first thing, of course, we go into the code and we have a look and see. We can see that it's subclassing active state. But further down in the class, all this particular thing is doing is turning game objects on and off. And so it's a bit hard to understand exactly what is going on with this particular component. So the next thing, of course, we'd probably do is have a look at the parent class. And that's describing some inherited structures as well. And it's also doing some other kinds of toggles and things like that. And it's a monobehavior. It's not subclassing anything else. This is the parent class, so we can see that it doesn't actually have anything to do with the puzzle side or puzzle sequencer. So the next thing we might want to look at then to find out what's going on here is we might want to look through our puzzle side itself to see what's happening. So because this is actually the last one in our sequence, we might find some clues from going to the second one in the sequence. It's called wait some time. This was actually a really crude puzzle side. It was a coroutine that waited for the number of seconds and then completed itself. That was all it did. It was really useful. So we have here some finish actions. So we have a set active state on finish here. So we're going to follow this thread and see where that takes us. So set active state on finish. So what we have here is we also have another array of active states. We don't have game objects anymore, we have active state objects. And we're marking these objects as some kind of active, but we're not actually enabling or disabling the game objects like we might think. And what is actually going on here, because I think I've drawn this out long enough, this is one of our puzzle helpers. So it's actually interesting that the active state puzzle helper was, I think, the glue that held the whole game together. Our game has 48 puzzles We made 48 puzzles in 8 months with this system, and I'm pretty sure this component was used in every single one of them. But what this particular one was, it was its own little independent state machine that would put our object into an active state, and where we saw the effect in our cat statue puzzle was when that purple button lit up after we cracked the statue open. And we did actually, in the end, have more puzzle helpers than we did puzzle sides, because generally they encapsulated small pieces of functionality that our puzzles required to be able to complete their puzzle sides, but they didn't want to be beholden to the sequencing of the system. And I'm going to show some more helpers in a little bit once I've dug through the code a little bit more. And some of the helpers did actually need their own little save states as well, which was where we saw helper restore events earlier. Now, active state was the most common usage of this particular helper. We did have a couple of other different variants. We had active state game object, active state material value, and we had some others that were more specific and covered by NDA. But it was different from most of the ones that used it, but the win, in this case, of course, the win button used it to make that button light up and telegraph to our player, this is a thing you can press now. But we're going to take a look at this active state helper in a little bit more detail, because in here are some of the lessons that I really wanted to include in this talk. So in here, you can see that we have an iActive state interface, which is only describing active and error states. And if you recall, if we saw this quickly, I'll just pop over here, you can see we have 4 states, in fact. And now we have an enum, which has those 4 states in it. And it's a bit of a question about what on earth is going on here, and the answer is tech debt. This is what happens when you don't think things through. So initially, when I started making the active state puzzle helper, I only thought that we were going to need things to be on or off, similar to the game objects. And like, I only need active and inactive, right? No, I don't need more than that. And of course, by the time I realised I do actually need more than that, the refactor wasn't worth it anymore, and so I just had to make the best of it. But other than that particular bit of awfulness, the structure of this is all pretty simple. There's a bunch of different states, set them, check them, toggle them, those sorts of things. And then, of course, at the bottom, we've got some virtual functions that we're setting up for subclassing purposes. So we're going to head back over to the active state game object that we saw earlier. So what's actually going on in here is pretty much all display stuff, because the parent class is handling all of the actual state toggles. And this, of course, is another example of where inheritance and interfaces were really strong for this particular kind of system, because this only needs to worry about what it looks like at this point. And one of the really interesting things about the active state puzzle helper was that while we've described it in the sense of active, inactive, error, and confirmation, we did, in fact, for a couple of our puzzles, actually have to subvert our own system, because we had a situation where one of our puzzle sides might require something that was in an active state to happen. But we wanted it to look as if the puzzle was in the inactive state when that happened. And I think you can probably guess what we did. We put the inactive visuals in the active state and the active visuals in the inactive one. And it worked really well. But that also highlights how much power there can be in a really simple system like this. Our puzzle sides were robust enough to not care about that sort of thing. You say you're active, I don't care what you look like, you're active, that's good enough for me. So I've covered off the entirety of all the really important parts of the puzzle sequencer, and now I'm going to hop over into an entirely different puzzle to show some of the more complex helpers that we used. So when we opened our little cat statue before, we saw that it had a bracelet inside. And the next puzzle in our definitely real game is a classic of every puzzle game forever. A combination lock. Now, our combination lock puzzle side was actually a really good example of a puzzle side that made excellent use of helpers. So I'm going to really quickly run this just to show you how to solve it. So we have this bracelet here, we have its 4 holographic projections, and we have some buttons here that our player can press to change what's on them. Now, of course, we've given our player all of their clues that they need to be able to solve this puzzle, but I'm not in the real game right now because it really exists, and I'm just going to solve this really quickly now. There. So now we've seen how it runs. Oh, there we go. And that's a different sequence finisher that you can see working there. So now we're going to have a look a bit more in detail into about how this works. So you can see in our puzzle sequencer component, you have two puzzle sides. The first one's called match combination. And you can see here we have some combination objects with a type of combination lock texture. So we're going to go into the first one here. And we have here combination lock texture with a matching symbol and something else linked here, which is called cycle through hologram symbols on tap. And I did say the name's got a bit ridiculous. So this was the cycle through kind of subsystem of puzzle helpers, and this was handling the interaction for each of the holographic screens. So you can see we have here a collider, and we have a bunch of symbols that we're cycling through, and we can see further down we have a very generically named puzzle component called do something on puzzle restore. Now, and then we have to invoke the events in that hookup. Now, you might remember that I called your attention in the puzzle sequencer to the restore puzzle sides. I always got this one mixed up in my rehearsals, and I think it was actually in the puzzle side. Yep, there it is. When we display our completed puzzle, we are also calling to all of our helper restore events, and they also controlled what they needed to do in those kinds of instances. But to understand what this particular one is actually doing, of course, we do need to dig into our event invocation. So this particular system was how we managed to set up the puzzle helpers to have their own little substates, because the helper could then be concerned with whatever kind of complex save state it needed to have, and it had its own function to apply that. I think we did usually call it restore puzzle helper, but the point was, because we were using Unity events in this particular instance, we didn't have to call it anything specific. We didn't even have to have this component. It was just completely optional for the ones that actually required. But we're going to have a look at what the restore puzzle helper is actually doing in this particular case. So pretty much we just have some link. We match the symbol to the texture of whatever's currently displayed on that specific hologram item. Remember, there were 4 of these running at any one time. We are populating a material property block with this one. And then we're running an initialize helper, which some of them needed, especially when we're using material property blocks, because the shaders would need things to be set up in a certain way. So we had to set that up as well. And then we have update object states, which you can see we're also calling up here in the cycle objects function, and you can see that's an override. And this was, of course, another little substate system. I think this actually went a couple of levels deep, because we had like cycle through on tap, and then cycle through hologram symbols on tap. And I do not want to know what I would have called it after that if I had to do another level of inheritance. It was getting ridiculous. It really, really was. And the reason we did that, of course, was because we had different ways of interacting with these particular objects depending on what that particular puzzle needed. So some of them would use a game object to enable and disable, and this particular one used a material property block in the shader. But we're going to hop back over to the combination lock puzzle now. So one of the really big benefits of having the system set up in this particular way was that you can see that as a result, the puzzle sequencer itself is kept really nice and neat. We only have 2 puzzle sides. Match the combination, hit the button, and that's all we need. But of course, the match combination puzzle side itself really was able to rely very heavily on all the interactions and substates that were facilitated by the helper, and its ability to have a standalone state that we could save out and also restore. And the puzzle helper restore system actually was a shoehorned in fix because of more lack of foresight. And that, of course, is the kind of thing that happens when you have to develop a system while you are also designing and creating puzzles using that system in a timeline of 8 months. And happily, it all turned out more or less okay, but I have definitely learned a lot. Hang on a second, I'm just going to stop mirroring. There we go. Okay. This is basically everything that I did want to cover in the puzzle sequencer, but I'm going to reiterate some of the main points. The sequencer itself was an overarching state controller which handed specific substate control off to the puzzle sides. Puzzle sides each handled their own save state and functionality, and we used puzzle finished actions to help manage what needed to be put into place so that the next puzzle side in our sequence wasn't in the correct state to be solved. Puzzle helpers handled independent functionality and sometimes used helper restore states if they happened to have complex save state requirements. And we also used an async scene loading and unloading system that dovetailed for us really nicely with Yarn Spinner and our hint system. This is probably one of the slides people want to take photos of if you're going to take photos of slides, so I'll give you all a second to do that. The next slide's one of those as well. So the next slide here is essentially the really basic flow of how the puzzle sequencer actually worked. And now I could have described this in a much more complex way, but I wanted to keep this really simple because it does very briefly describe exactly the flow that our whole game's going to go through. The next thing I want to cover is what I would do differently if I was going to make this system again. Now, of course, I would definitely think a lot more carefully about the active state subsystem. I would avoid using that horrific internal bull that I should never have thought of in the first place. And I would probably be a lot more considered, with the helper restore state functionality. And I might make the puzzle helpers use an interface or another kind of set of inheritance of their own. But I also feel like the puzzle helpers themselves, I feel like there was a really big benefit in them being able to be very outside that whole ecosystem and have control of their own events and have control of their own systems, and maybe that's actually where their strength lay. So that is actually all of the content that I was going to cover. So now it is time for any questions if anybody has any. Yep, over there.
Yep. I was just wondering how you conveyed to the designers which of the classes in the down levels of inheritance to use for each of the puzzles.
That's a good question. So the question was, how did I convey to the designers which of the components in the various levels of inheritance they should be using for their puzzles? And as it happened, we had a lot more programmers and designers in our team in the end, and it was a small team, as you saw. There were not many names on our list, and that was almost the entirety of the project team. So I would brief the designer personally usually. We had documentation, of course, that was very badly maintained, but for the most part, what ended up happening is the programmers would make the puzzles and the designers would tune them. Any other questions? Yep.
I'm curious what the rationale behind using mono-behavior inheritance for all of your helpers and puzzle sides as opposed to using something like scriptable objects or just a base class.
I'm very new at this. The question, by the way, was what was the rationale behind using mono-behavior inheritance rather than scriptable objects or something like that? And the answer is I'm very new at this. I use scriptable objects a lot more now, but I've only become a senior fairly recently, and so I am still learning about all those sorts of things that might be available to me. Any more questions? Yep, over there on the side.
Thank you. Thank you. I was wondering what considerations you might have made to making sure that the puzzle didn't accidentally progress through its states, like due to accidental double clicking or that kind of thing, because that's something that I've run into as an issue before, is controlling when it can be interacted with.
That's a good question. So the question was on the mic, but I'll repeat it anyway. How do we make sure that the puzzle sides couldn't be progressed accidentally with accidental double clicks or things like that? And all I can say is that was not a consideration for the platform we used. I'm sorry. Just here.
Yeah, did you have any special tools for debugging the puzzles?
Did we have any special tools for debugging the puzzles? We, in fact, do have a very special tool at Mighty Games. It's called Mighty Build and Test. And our test bots were actually highly useful for this particular situation because they were soak testing our puzzles permanently, like 24 hours a day, and whenever any bugs came up, we were able to hop onto them very quickly. But we did have human QA. We all play tested the puzzles ourselves as well, of course.
Yeah, because I was thinking during the development of that, you've got a lot of logic hidden away in the data within a scene, don't you? And there must be times where you're thinking, this isn't quite working how I want it to be. And, looking through the variables by looking through one game object at a time can be a bit kind of tricky, can't it?
Yeah. The test bots were very useful to us. Any more questions? Does not. Oh, I can see one all the way up the back there.
Given more time and, say, more budgeting and whatnot, would you have considered a different approach to like the traditional inheritance and polymorphism flow that you already have going on? Because it feels to me like one major drawback of this entire approach is that it works really well with this kind of niche use case that you're delving into as you build a puzzle game, but at the same time, it kind of locks you into that specific use case, and it doesn't feel like it will translate to another project that does something slightly different, so to speak.
That is a fair assessment, and I haven't had to solve that problem. All right, I think that's all the questions. Thank you all very much for coming. Oh, one more question. Oh, so sorry, I didn't see you there.
So I see you mentioned using async at the end there, but earlier you were talking about using coroutines and checking for clicks in update. Is there a reason why you didn't use async throughout the whole project to accomplish those same things, to reduce the overhead? Or?
So the question was, we used some async scene and unloading, but there's also some clicks in update and coroutines and things like that. And the question was, is there a reason why you didn't use async through the whole project? And the answer is more or less, I'm very new at this. All right, thank you very much for coming today.